we can just edit what we need. Yeah.
If I could sneak out after 20 minutes.
Oh.
I promise not to bang the
Well, maybe I should go this way. Don't mind.
Someone's going to use that. That Lewis is doing it. He's not. Yes, he's still using it. More chairs down there.
Yeah, it was next
Okay, it's 4 o'clock sharp, and we can start right now. And great pleasure to welcome Wojciech Zurek, who is a fellow at the Salmos National Lab, and he's going to tell us about our quantum mechanics stuff. And importantly, Wojciech is visiting KITP, and he'll be here till the end of the week. So if you'd like to ambush him with some questions, you know where to find him.
Thank you for the extensive introduction. It's a pleasure to be here. I had the pleasure to be in the audience many times, and so I'm here to reciprocate. Let me start by saying that even though it's a colloquium, I do appreciate and welcome questions in course of the colloquium. Now, while I welcome questions, I reserve the right to suppress them. So, the subject of my talk is quantum theory of the classical.
Classical what?
So let me give you now what I have written down to myself, which may help. We know that our universe is quantum, but we believe that we live in a classical world. So a contrast between what we know is at the foundation and what we know we perceive is what I would like to address. Does it answer?
Okay, we will see.
Okay. What I will start with is discussion of decoherence. I have a feeling this subject is known to many of you. And so it will be a brief discussion, and I will just hit a few key points. I will then express dissatisfaction with decoherence as the ultimate answer. And I will go on to tell you why I'm not completely satisfied. And I will talk about emergence of the classical from quantum at the level more fundamental than what is offered by decoherence. Part that I will not get into is origins of objective realities. Would take longer than the 1 hour allotted here. By the way, brief reviews of this are, and I especially recommend the one. Is there a point? This is a pointer, I presume, right?
Yes.
Okay. Brief reviews were published, including the one that I recommend most in Physics Today, October a few years ago. Let me start with a quote from Albert Einstein, who worried throughout his life about the theory he helped bring to life. He didn't like quantum mechanics, and everyone knows it, and here is a letter he wrote to Max Born a year before Einstein died. So here he says, let psi1 and psi2 be two solutions of the same Schrödinger equation. When the system is a macro system, and when psi1 and psi2 are narrow with respect to position, so here we have macro system, and it sits right here, but it could be sitting also right here. Then, in by far the greater number of cases, this is no longer true for the superposition. So a superposition of a bottle here and a bottle there is neither here nor there. Narrow, and yet these states are still solutions of the same Schrödinger equation. So narrowness with respect to macro coordinates, Einstein concludes, is not only independent of the principles of quantum mechanics, but is moreover incompatible with them. So that is really the statement of the problems that we are trying to address. And we know exotic examples, including domesticated animals, that I shall not delve into. One good quote deserves another. Space is big, really big. You just won't believe how hugely mind-bogglingly big it is. Where is this from?
Hitchhiker's Guide.
Yeah, you guys know literature. I'm gonna append it only slightly. So this is really the other way of stating what the problem is. There is this huge space of quantum possibilities. Every superposition of every superposition is a legal quantum state. And somehow, out of all of these states, bottles which could be in superpositions all over the place, emerge a much smaller set of classical states, which are, for example, localized. So our aim is to understand how out of this enormous range of possibilities, we end up with things we encounter in our classical world. In other words, again, our universe is quantum, yet we live in a world which appears to be classical. Here's the answer, and it's very telegraphic discussion of decoherence. Decoherence recognizes that systems, especially macroscopic systems, the ones we tend to encounter, are not isolated. They interact incessantly with their environment. That interaction has consequences. So, for example, if you have a system which is in some arbitrary initial state in its Hilbert space, and is initially not correlated with the initial state of the environment, then as a result of interaction, and this is just Schrödinger equation applied to both the system and the environment, you will end up entangling the system and the environment. This entangled state, still pure, describes both of them. But we are generally not interested in the state of the environment, and moreover, often state of the environment becomes inaccessible. Therefore, what we are resigned to work with is the objects that describe the state of the system alone. That is the reduced density matrix. Reduced density matrix is obtained by tracing over the states of the environment this pure state. So this density matrix is an object which we interpret as a statistical distribution over states of the system. That's an old story. Landau, I think, was the one who introduced reduced density matrices in 1927. What has not been appreciated is that if you take into account typical interactions we have in our universe, then the states which will end up on the diagonal of the density matrix are always the same. And in particular, the yellow colors. Right? So there is a special set of states which has a property that they are resilient to the interaction with the environment. If we started in one of them, nothing would happen. It would stay the same. This means that there is a set of states which are indeed selected by the interaction. I call this environment-induced super-selection or Forshort-Line selection. The preferred states which are immune to the interaction with the environment, I call pointer states. The name has to do with the fact that pointer of the apparatus better be in one of these states. It better be immune, even though it's plugged in the wall, being hit by photons, etc. Question.
Are these different than the eigenstates of the system?
They are different than the eigenstates. They are generally not the eigenstates of the system. Okay, and next transparency will tell you how we go after them. And we don't always, they are not guaranteed to exist always, for every situation. So, stable states eventually appear on the diagonal of density matrix after the coherence time. They are effectively classical, at least in the sense that they are immune to the interaction with the environment. Pointers that are left unperturbed by environmental monitoring. So, you know, you look and you see something in a state, you look back and you look at it again and it's in the same state. This is what we expect of the states that are classical. Interaction Hamiltonian between the system and the environment is actually a bigger say in what these states are. But they are often negotiated between the two, depending on the strength and properties. In particular, if you had no self-Hamiltonian of the system, just the interaction Hamiltonian, then the states which commute with that interaction Hamiltonian obviously would have this property. If you start in one of them, nothing would happen. So the interaction Hamiltonian matters. It helps select you pointer states. This is a condition that in simple cases applies. And let's remember the fact that we needed to take a trace in order to get reduced density matrix, and that we took for granted that this reduced density matrix is a statistical object that describes the state of the system alone after the environment has been traced out. Very simple example. So, my system is a spin. It can be in superposition of up and down states, so 0 and 1. Its density matrix initially is simply projection operator corresponding to this initial state. So it has this form. Off-diagonal terms are essentially as big as the on-diagonal terms. Let me insert it in the environment of other spins. And for example, I take a bunch of other spins interacting with my system spin with the interaction which is diagonal in the 0, 1 basis of this bit. If this interaction takes some time and if the environment is big, you will end up with a density matrix where the off-diagonal terms are very close to 0. They are suppressed. On-diagonal terms are not touched. So this is an example of environment-induced superselection, line selection. Pointer observable correlates with the environment, and it defines pointer states that survive decoherence. Phases between pointer states are lost. You can look for these special states, pointer states, by basically turning into equations what I've said. You want to look for states which are immune to the interaction with the environment. So for example, and I call this strategy predictability sieve, you can list every state in a Hilbert set of the system that you are interested in. I mean every state, not just some basis. All superpositions of all superpositions. And you let them evolve